Hey guys, this is Professor Janacek, and I want to go over some physical applications of integration. So, example number 2 here. How much work is needed to pump all the water out of a cylindrical tank with a height of 10 meters and a radius of 5 meters if the water is pumped to an overflow pipe that is 15 meters above the bottom of the tank? So I've gone ahead and drawn this here. We've got a cylindrical tank, and there's this overflow here at the top, and I know that the height of the tank itself is 10, but 5 meters above that is where that overflow is, and so that gives me a total height of 15. I want to point out that I have decided to make, for ease of use, I've decided to put my axes, my x-axis is along the bottom, so then I can deal with the heights of 10 and 15 quite easily. And my y-axis I decided to put right in the center so that I can deal with a circle that has a radius of 5. So that I don't have to worry about going 5 and then another 5 for the diameter. I can just think of the radius in terms of that 5. All right, so let's get started. We are looking at work. And this is actually work that's being lifted. So we're going to use, work from lifting. So that's the equation W is the integral from a to b of rho times g times a of y times d of y, dy. All right, so remember rho is our density, and this is for water. We should know that one. The density of water is 1,000 kilograms per meter squared. Meters cubed, there we go. G is gravity, acceleration due to gravity, which is 9.8 meters per second squared. All right, and then let's see, A of y, that's a function, and that's our area. The area in this case, so we're looking at our circles, right? The area across here is a circle. So the area of a circle is pi r squared. In this case, that's pi times the radius, which is 5 squared. So we get 25 pi. And then d is the distance that it's being lifted. D of y, again, a function of y. All right, so in this case, it's being lifted, well, when it's full, it's only going to be lifted a short amount. When it's empty, it's going to be lifted a much longer amount. So this will vary, so I will need my variable. Now let's take a look at, suppose I'm just looking at where it is now, where I've got that water level drawn. That's the distance it's going to have to be lifted. So remember, this whole bit is 15, but this bit is an unknown. I'll call that unknown y. So I am going to look at that distance is the whole thing, 15 minus my little unknown, and that's going to give me this little bit here left over. So my distance is 15 minus y. All right, so now to set up our integral, I think the only thing I need is to figure out where I'm integrating from. What are my limits of integration? Well, I'm going to integrate across this whole cylinder, so from the bottom up to the top. That's what I'm integrating from. So that looks like I'm going to integrate from 0 up to 10, because it's only the height of the cylinder. from the base of the cylinder up to the top of the cylinder. All right, and now let's go ahead and fill in everything. Oops. Rho is 1,000 times G is 9.8. A is 25 pi. All of these are constants. How nice. D is 15 minus y. There's my only variable. So when it comes to integrating this, we could go ahead and factor out all of those constants. And all we really need to integrate, oh, isn't this nice? I just need to integrate 15 minus y dy. Evaluate that from, that's from 0 to 10. Oh, that's going to be so easy. I will let you have fun with that. Shouldn't be too difficult. Lots of multiplication. Where did we go? Here we are. Lots of multiplication, but that shouldn't be too bad. You should end up with 7.7 times 10 to the 7th. Of course, this is work, so it will be in joules. All right, have fun with that one. Okay, let's see. This got a little out of whack. All right, for example 3, we have a large vertical dam in the shape of a symmetric trapezoid that has a width of 20 meters at its base and a width of 40 meters at the top, and the height is 30 meters. We want to know the total force on the face of the dam when the reservoir is full. So notice how I've drawn this. Again, it is a symmetric trapezoid, meaning that the left side is symmetric to the right side. That's how I have this drawn. To make life easy, I've put the y-axis here in the center, so I can use that symmetry to my benefit. The base is the smaller one. The base, notice, is 20 meters. The height, the top of it, the width of the top, that's 40 meters. Also notice how I've done that. Because my y-axis is here in the middle, then the base is 20 meters, so that goes from -10 to +10. Notice I split that evenly, 10 on one side, 10 on the other. And the top, 40 meters, so again I split that, so it goes from -20 to +20, so that's where I'm using those values down there. Again, -20 to +20, that's 40 meter difference. All right, and then of course the height here, not the edge, it's not measuring the edge, not that bit, but the height, that is 30 meters. Okay, and we're looking for the total force on the face of this dam, so we want to use our force equation. So it's the integral from 0 to b of rho g b minus y times w of y dy. All right, so in this case, rho, again, this is density, and we are looking at water. Again, we should have that one down. It's 1,000 kilograms per meter cubed. G, again, is acceleration due to gravity. We should know that one as well. That is 9.8 meters per second squared. In this case, this b minus y portion, y is our height, so that will be 30 minus y. And then w of y is the width. So remember, this is the height, whereas w is the width. Okay, now this one could be a little more challenging. Let's take a look at this width. So that's this whole bit here. Now I notice that I have marked here that this thing is an x, so my width will be 2x. But this has to be a function of y, so I have to write it somehow in terms of y. Well, let's see. This is the x values, and of course those will change each time, each point. So I need to find the y values, the height. So here, This point, what is the y value? And what is the y value here? What is the y value there? Oh, that looks like I'm looking for y values along this line. Meaning I need to find the equation of the line. And I'll use the two endpoints there. Through the points, we've got what? 10, 0 is this first point. And the top point there is the point 20, 30. Take a moment and find the equation of that line. Pause this if you need. You should come up with y is equal to 3x minus 30 using traditional equation of line techniques. But don't forget, we need to write this in terms of y. So I'm going to write it as x equals, what is that, 1/3 times x plus 30. So there's the x value. Of course, remember our width is actually 2 times that. So it's 2 times 1/3 times x plus 30. So all in all, I'm sorry, wait, that's not an x, that's a y. Oh dear. Y plus 30. Y plus 30. There we go. So all in all, our width is 2 times 1/3, which is 2/3, times y plus 30. Okay, so now if we put that into our equation here, we're going from 0 again. B is our height. So that's from 0 to 30 of 1,000 times 9.8 times 30 minus y times 2/3 y plus 30 dy. Of course, before doing all this, I think it's a good idea to go ahead and factor out all of these constants. All that would be left inside the integrand is 30 minus y times y plus 30. All the others can be factored out. Of course, we could multiply those. And that means our integrand, let's see, 30 minus y times y plus 30 multiplied, distribute, however you want to say it, we would end up with, what is that, 900 minus y squared. And that shouldn't be too difficult. After you do all that integration, evaluate it from 0 to 30, multiply by all those coefficients there in the front, what you should end up with is 1.18 times 10 to the 8th. And this is a force. And so that would be in terms of newtons, uppercase N. There you go. Enjoy.